So here we are, the band theory of solids, and it is also sometimes referred as band theory of semiconductors. So this has got its root both in physics and chemistry. So this is a field where the process that you find in chemistry can meet the standards in the physics. And here it says the band theory of solids is different from others because the atoms are arranged very close to each other, such that the energy levels of the outermost orbital electrons are affected. First, what is a band? If you have two lines, if you have two lines or two regions with some property, then it is called as a band. In chromatographic techniques, we also use the eluent and we also use the uh, solutions and solvent. When something dissolves first, it comes out as a band, so that is also a band. And in the U visible spectrum, you have got 350 to 700 the visible spectrum, and within that we have got 350 to 450 as ultraviolet region, so that is also called as a band. In band theory of solids, there are many energy bands, but the following are the most three important in the solid bands, in the energy bands in the solids. So I think we know about the valence, we know about the conduction, and we know about the forbidden band. When you take up the molecular level, atomic level, we got a nucleus at the center, and this nucleus contains the protons and neutrons, and we are not bothered about that, and our concern will be only with the electron that is in the outermost orbital. So we also know very well that when this electron, in the last level of electrons is called as the valence electron, and this is the place where most of our chemistry resides and where we have most of the reactions, most of the excitations, most of the decompositions taking place. So when there are other levels of the electrons which are not involved in bonding that reside inside and that we are not bothered about, and the valence electron, they just, if you just draw it like this, they have got certain energy, they have got certain limit also. What is the limit? They can get excited to certain level and then come back. So we define this by means of some energy levels. So this is a representation. I think you should know about the representations, and if you know internuclear distance. Okay. So if you increase the internuclear distance, bring them together, the energy level, it decreases and it rises. You can have this, then there is a continuum. That is, the energy goes on decreasing if you increase the internuclear distance. After that, it can increase and then decompose. Then decompose. So you must know this energy always in the upper level and internuclear distance, distance between two atoms. So when you increase the distance between two atoms, the energy is found to decrease first, and then it. How long can you stretch this? Unless there is certain limit by which these can be held together. So after that it breaks. So that break is what you call it as the continuum there. So there is a limit for the electron to get go to the higher level, and that level is what we call it as the conduction band there. In the conduction band, the electrons are free. So if you have got two levels of such things, let me draw another nuclear proton and another atom there. Here it is. So if I have an electron belonging to this, what happens is after I excite them to a particular level, the electron goes there. And what happens is this electron can, it used to be initially revolving around this, but it can take up this level. When it goes into this level, this electron can just simply go into this and it can take up this level. Okay, so it is called as the foray. So when does this kind of thing enter? These kind of things enter when you have when you exit the electrons into the conduction band. So here they are free to move about. And before that, they are held together by electrostatic forces or the nuclear charge forces. The electron is not allowed to be free by the positive charges held by the nucleus. So you can excite them or you can bring them, and then we're going to see how these things happens when there is a buildup of the bond there. The forbidden band is referred as a band where electrons are not allowed to go. Electrons are not allowed to go. That means, there is a place where electrons can go. So they will have some higher energy, their moment of freedom will be very high, and this nowadays in chemistry it is called as the Rydberg level. A Rydberg level is a place where excited electrons can go and do their work. What do the excited electrons can do? They can simply move over from one nucleus to the other nucleus. So as a result, I'm just going to draw a diagram there here where we can see the different atoms and their their electrons. Okay, so I'm just drawing a graph to suggest that suppose if you have atom 1, its nucleus will be, and its electronic level will be, just imagine like this, another electronic level like this, another electronic level like this, another electronic level like this. So I'm just going to have different electrons. So this is n number of atoms, it keeps on moving, and this is the energy. So as we go up the energy increases. So I'm just putting the nucleus here, the nucleus there. Okay, the nucleus at the center, nucleus at the center, and this happens to be the place where electron can reside. Electron simply revolves. So I'm just scaling it. I'm just descaling it so that if electron moment can go, it can just go over like this and make a circular motion like this. Okay, and the same thing is with the nucleus also. Just for energy profile, I'm just forgetting this, taking up the electron. So even if it goes from electron from this place to this place, that also is there. So I'll draw a level. This level is I'll just indicate some energy level, which I can call it as the valence level. Okay, what happens is there is another level that exists. So this is the Rydberg level, or this is the conduction band. When you heat it, the process of absorption of energy takes place and by means of the thermal radiations or by means of ultraviolet radiations. These electrons can simply get excited into the top level. Okay, so likewise, you can have this electron going there and this electron going there and this electron going there. And when these electrons go there, the the attractive force is held together between this. It is very small at the beginning, and then when electron goes there, the electrostatic forces between the nucleus and electron is increasing, is decreasing, and the hold of the electron is lost. So now it can move to this place, and if it moves to this place, this electron can move to this place, and this electron can move to this place, and this can move to this place, and there is a okay. You can have, if you have n number of atoms, you can have a sea of electrons just moving together along this band. Okay, that means this particular part becomes a band now. Now it is also in physics, it is also called as the Fermi band, or the Fermi energy level, where the electrons, the band will be empty and the band will be a place where you can imagine something like a classroom where you've got a strength of about 50 students, and then you've got 10 benches there. So if 45 students stand up, 45, 9 benches will be occupied, one of the bench will be vacant. So there will be always a vacant bench in every class, and maybe for the reason of the absence of the students. The same thing exists for the band also. There may be empty bands, energy bands. So likewise, you have got several levels existing above that. So conduction band, Rydberg level band, and the forbidden bands there, they do not go, but they do go. Why? Because when you give certain energy, they can go. Now you can give certain energy so that that electron can escape forever. That is called as the decomposition energy, and that is the energy which is the ionization energy. The ionization energy, if you give, it can just to go out, get ionized, and the nucleus can exist in the cationic state. Okay, that becomes a different part of the chemistry. But this is the thing that happens there when you have put n atoms. Suppose if you put 1,000 such atoms there, then thousands such electrons will be available to freely move about. Now when you have free movement of electrons, free movement of electrons constitute the free movement of electrons constitute or they are responsible for the electricity. Okay, so you know an electronic moment is electromotive force is required for the movement of the electrons. So let us see what this thing is to describe about the bands there. So you have got conduction band, the energy band that consists of free electrons and energy levels is known as the conduction band. For electrons to be free, external energy must be applied. That is, external energy means heat and even sometimes light you can just, and it can be pushed into the conduction band there. Okay. So likewise, you know the valence band is there. They are loosely bound to the nucleus of the atom. This is the region where our chemistry is taking place. The energy gap between the valence and the conduction band is known as the forbidden band. I'm going to show you this in the adjacent pictures now. So you keep in mind what is this forbidden gap and the conduction gap. So the electrical conductivity of solid is determined from the forbidden gap and also the classification of the materials as conductors, semiconductors, and insulators. So this is the property that we are going to see as conductors, semiconductors, and insulators. Right? The insulators, you know, are these are the three things which I'm going to just explain by taking the an example of the sodium atom there. Here it is. So you can see that energy level increases in the sodium atom. You got 1s2, 2s2, 2p6, and 3s1. These levels are there. This is the core level, and this is the next level there, and this is the valence level. So you'll have k element shell there and valence level. In the valence level, you can see that there is one electron. This electron is free to move about, and when you have five such sodium atoms together, the 3s level, you know, this is it. This is the 3s level. Just can see how it is represented by means of the diagram. Split to five separate energies. The three energy levels falls in between for two sodiums, and there are five electrons occupying these energy levels. That is what it says is when you have five sodium atoms. This is for single sodium atom. Okay. So when you have five sodium atoms, you can represent it to five different energy levels. So as the internuclear distance between these two atoms increases, as you increase, the levels simply merge. What it says is you put one more electron there. Here it is. One electron there, 2s electrons. So there is a distance between these two. Okay, when you just join them together, this is between these two. And here is the distance between this is the second atom. In the first one, you have got only one level, one pair of electrons, but when you have two atoms, it consists of the two levels of such thing. So when you have third atom, it may even come up here like this, and that is how we have got the building up of the electrons, and this is the 1, 2, 3, 4, and 5 that gives rise to a diagram like this, which is seen in. You have five levels there. Initially, there will be five different energy levels, but what happens is as the distance is increasing, you have to imagine how the energy level goes down when you increase the distance. So distance means if it is like this, the energy is like this. Okay, like this. Now you just increase the distance, the energy is like this. Now you just increase some more distance, the energy is like this. So when you increase, the energy is getting increased because of so many electrons. Then there will be limit for that. Okay, so that is that entire thing we just shadow it, you know, into a particular thing region called as the this is a region where the uh, this is a region where you know we have got available states, and these are not the field states, these are the benches where students can occupy. That is the region where the student can the region where the electrons can simply go and stay. So when you bring n atoms, n means you know it may be 50 or 5,000 atoms, such things bring together, this particular gap, you know, region is increasing. energy increasing, and this is a free space. This is what we call it as the band. That is why you have this particular band. The resulting energy is a band containing n very close the space energy level. There are now n electrons occupying 3s band. Why 3s? This is the valence band. We are not taking 2p because it goes inside. It is very tightly held by the nucleus. Therefore, it is not free to move about. So let us see what happens next. Now this is the made up of three. If you take three atoms, as we have seen that there is a building up of these electrons there. The levels alone are shown here, not the electrons, because it's getting uh, some kind of some uh, density increase in there, and then this, when you put up certain levels, you can see that the 3p energy level is also approaching there. That means some of the electrons can just go and put in the 3p electrons also. Now let's take a closer look at the energy levels in the solid sodium. Remember 3s is the outermost level. When sodium atoms are brought within about 1 nanometer of each other, the 3s level, the individual atoms overlap enough to begin a formation of a 3s band. This is the 3s band there. Okay. Now you can see that 3s band is overlapping with the 3p band. Already 3p band doesn't exist. There are no 3p electrons for sodium. No 3p electrons for sodium. But what happens is there, when you just put up more and more electrons like this, it is touching the region where 3p start. Okay, so you can call that the s electrons are behaving like a p electrons. So if I say that sodium atom is having p electrons, and I am right, because at a particular energy level they behave like a p electrons, and that results in the building up of the band like a 3p band like this. So here the hold put together by the nucleus is loosened. Is loosened. So as it loosens, the hold loosens means the attractive force between these two is decreased. So it is free to move about. The electron from one nucleus is able to move there, and this electron from another nucleus can move there. So that is represented by a particular band here. 2p band here, 3s band here, 3p band here. Note that 3p electrons do not exist, but as you build up some of the energy levels and the energy levels increases, it touches the 3p band, and at times if you have got so much build up, you can also see 3d bands. Usually 3d exists for transition metals only, not for the alkali metals, but the electrons can behave in such a way that you can call it as a d electronic behavior, and this is the present chemistry where you can classify the sodium atom as a transition metal for a brief amount of time, but at a higher energy level. Okay, so as you go up, as you build more and more electrons there, you can see that this is a kind of a band appears, and this is called as the energy band. So up to this is the core level, and you got only 3s level, where you just put more and more atoms there, sodium and sodium and sodium atom metal is there. Just if you put it, there is a band that you call it as the 3s, and then above that you have got a 3p. They just do not go there, but if you put some more energy, there is no space for them to occupy here, and they can go to this particular place. And in between there exists a particular band which you can call it as the Fermi gap, because it is a region where electrons can freely move about. Okay, the energy, the attractive energy put forth by the nucleus is lowered there at that particular place, and so that is shown here by this particular diagram. It's a very good diagram. You have to draw it in the examination. Highly schematic diagram. So 1s level, 2s, 2p, 3, all these things are there. Okay, 1s, 2s, 2p, all these belong to the core level, and the difference in energy is also there. And when you go to this 3s, and the 3s energy band contains twice as many states as there are electrons. The band is half full. Okay, what does it mean? The band contains twice as many states. States means it is, you can imagine, if you have a molecule, you can imagine the orbitals. There are more orbitals than less electrons, then you can call it as a half occupied. If you have more electrons than the band, then you can call it as a overflow of the electrons. So it touches the 3p band also, but here there is sufficient space, so it is not fulfilled. At T equal to 0, what is the T is temperature equal to 0, is filled exactly half F, and the Fermi level EF is right in the middle of them, and this is called as the Fermi level. Okay, some people call it as the Rydberg state. Remember, the excited state exists here. Okay, we often study our entire chemistry. 100% of our chemistry is only 99% of our chemistry is only with the Rydberg state only, where the electrons we excite them and then we study their behavior. The rest of the chemistry we study is belonging to the nuclear chemistry, and that is only for the nuclear reactions only. So here we are concerned only with the last electrons in a particular way. Sodium metal is because of an applied field can easily give energy to excited. Now you just put some energy there, free movement of the electrons there. When there is a movement of electrons, it constitutes the electricity there. Look at what is happening here inside a molecule made up of a number of atoms. The energy band, this and this, is getting closer as you put more and more electrons there. Okay, so that I'm going to classify it here in a different diagram there. I am putting a band which we call it as a conduction band and valence band. Conduction band and valence band. So some electrons are here, no electrons here initially, and the gap is very large there. Okay, because the gap is very large, I'm calling it as an insulator. Then what happens is that you just fill up more and more electrons there, the buildup of the valence electron increases. As it increases, the conduction band and the valence band, they just shorten up. Okay, this is a small gap there. Small gap there. Now what happens is that if you raise it by some amount of temperature, some heat, the electrons can flow from this to the conduction band. When they flow to the conduction band, they are free to move, and the semiconductor becomes a conductor. So at higher temperature, semiconductor becomes a conductor. That is the most important point that you have to write. At higher temperature, a semiconductor becomes a conductor. The reverse is true for the insulator. If you heat the insulator, there is no use at all. But if you heat the semiconductor, it becomes a conductor. And if you heat you can see that more and more electrons, if you the band gap is becoming very small. So this is a conductor, therefore. This is a conductor. So if you have a conductor, if you heat the conductor, it becomes an insulator. Why? Because you are deviating the electrons from different regions, and you know very well, heat is one thing that reduces the efficiency. Reduces efficiency. This is the thermodynamic factor. Okay. Now the energy bands of solids is given here. The conduction band and valence band, large energy gap between the conduction and valence band, doesn't allow the electrons to move from here to here. It is not allowed. And in the semiconductor, the band gap is very small, and this is called as the Fermi level. And in the conduction band, these are overlapping. So this is overlapping actually, and these things overlap. The conduction is taking place. So this is the band theory of conductors, and you can see that I put some electrons there. These are all the electrons here. Okay, electrons here in the conduction, in the valence band here, and then this is the conduction band. And when this temperature is increasing to about 300 K, some electrons simply move up here, they are free to move. Okay, so free to move constitutes conduction. I think it is now clear for you how the band theory of solids, band theory of semiconductors explains the uh, conductivity in a particular molecule. You have to draw these bands to explain all these things, and you can take up the examples with the what is that? That's the sodium, and some energy graphs are there. So another thing that I want to tell you is this is the case with the some of the organic things also there. Okay, organic things means organic semiconductor is there. What you are holding in your hands as a cell phone is actually this is time being inorganic material. inorganic material, and you can have organic material. What we call as organic light emitting diode. OLEDs are there. QOLED is there. Nowadays, you have got some increasing. What happens is you are increasing the conduction band using organic molecules instead of the inorganic molecules. So these are all the inorganic molecules: sodium and other semiconductors, and silicon, germanium. You got all the semiconductors. When you heat the semiconductors, it becomes a conductor, and this is one of the factor why you have got computers in ordinary place. Earlier, computers used to be placed only in the air-conditioned room because conductors became insulators at a higher temperature. So you have got you got semiconductors at room temperature. When the temperature increases, they become conductors. So we need conductors for electricity. Okay, thank you for joining me. See you soon with us with another organic light emitting subject.